So today we are going to learn about do more recursion problems. I'm still going to figure out I still actually got to figure out what your lab's going to be for this week, because I'm not sure if I have one ready. So I'll see what your homework assignment will be this week. But I'm thinking. But if I give something out, I mean, I'll figure it out. I'll try not to make it like too oppressive, especially since you've got an exam rather than a lab. So let's go ahead and start this. So then we're going to go over linked lists recursively, and then I'll go over in this class. I will try to go over some of the harder problems from the exam, from the practice exam. So you get one sheet of letter or A4 paper. So if you don't know what letter is, then A4. So in other words, a standard sheet of paper, right? Front and back. Front and back, handwritten, typed, I don't care, right? You can do what you want. If you need to bring in a magnifying glass in order to use your paper effectively, then that's your prerogative, right? So we are going to learn. Let's get back into chapter 5, but we've got a lot of exciting, fun stuff today. The first thing we're going to learn about is, so I left off, right, on Fibonacci, right? We left off with Fibonacci, and did we get to the point, we discovered that it was terrible, right? Right? Did we discover that it was terrible, right? That I tried to run it, or no? Was I just talking about the method? So let's go ahead and see where our code is. So boom, classroom, destruct code. Recursion evening, recursion examples. Here we go. So did I write it? Yeah, I wrote it. And so, yeah, I wrote it. And let's go ahead and see what we did. We ran fib of 40. And remember, the Fibonacci sequence is that it is that the nth Fibonacci number is the sum of the n-1 and the n-2 Fibonacci numbers. So that kind of makes it a perfect recursive definition. In fact, it's the first recursive definition I know, that I learned, even though it's terrible. And I'll show you what I mean by terrible in just a second. So ran it, it runs pretty fine for the first, for so forth on this computer, right? My computer's actually nice and quick when it comes to this stuff. And if I run at 40, there's a little bit of a lag when I do that. 41, there's a little bit more of a lag. And once I go up to 42, trying to calculate the 42nd Fibonacci number, it starts to become much more noticeable. And at 44, it starts to become really noticeable. And at 50, as we're about to see, it's going to take freaking ever to finish. Okay? Now, why is that? Well, the Fibonacci function is different than the other recursive functions that we've learned. Because all the other recursive functions, right, they have their base case, and then they have the recursive case, right? But the recursive case only makes one recursive call, right? The Fibonacci, and you can, if you got close, you'd be able to hear the fans going now. If you got close to the, to here, sorry, oh, there it is. So that took a while. So if you look over here, we have a recursive call where we calculate the n-1 Fibonacci number, and we have a recursive call that looks at the n-2 Fibonacci number. So in other words, if we were looking at the fifth, this example over here, trying to calculate the fifth Fibonacci number, to calculate the fifth Fibonacci number, we got to calculate the fourth Fibonacci number, then the third Fibonacci number. Okay, if we're going to do that, we need to calculate. To calculate the fourth, we need to calculate the third and the second. And to calculate and that just is going to be, that's going to return 1 because that's 1. And then to calculate the third, we have to calculate the second and the first. But over here, I have to calculate the third Fibonacci number, even though in this call, I already calculated it, right? Does that make sense? So the idea here is that basically I'm redoing all. Not only am I making for 2 calls for every recursive call, I have to redo a bunch of work that I've already done, right? So the idea here is that now if I calculate the 6th Fibonacci number, right, that's going to calculate the 5th Fibonacci number and the 4th. So I'm going to duplicate this entire branch on the right side of that new tree. So the runtime for this is approximately O of 2 to the nth power, right? Because every time I add another call, it's going to take about twice as long. So that means that when I went from 40 to 50, right, when I calculated my time, right, when I ran this on 40, that was, that was a slight little pause there, okay? But now, when I go up to 50, well, that's not 10 times longer or 25% longer. It is 2 to the 10th times longer, which is about 1,000 times longer. So this took about 1,000 times long as the 40 call, right? So that's and 1,000 times longer. That's not too much when we're starting from milliseconds, right? That just brings it to seconds, right? But when we're talking about like minutes, that's gonna take a while, right? You'd be surprised how few hours there are actually in a year, right? So it takes a while. There's a couple ways to solve this. The first, which you should learn about in other contexts, is what we call tail recursion, where basically what we do is that it's a very interesting statement. Look over here. Private static in Fibo. Fib current. So the current, where it takes as an argument the current Fibonacci number, the previous Fibonacci number, and n, where it calculates the nth Fibonacci number, right? So if n is equal to 1, return 1. So here, what it does is that in order to calculate it, so what it does is that it returns fib plus, the current Fibonacci number plus the previous Fibonacci number, right? So it passes that in as an argument. It passes the nth Fibonacci number in as an argument plus the n minus 1 Fibonacci number to the function, so that it can use that to calculate the n plus 1 Fibonacci number, right? So it's kind of building it up. And it starts with 1 and 0. What we use is a wrapper method, which we'll see how to use that effectively. So this one's clever because it's building it up and it's storing the information in the parameters. That's kind of fascinating. That's really weird, and how to build those is a long discussion I don't want to waste too much time on, but it's like one of those really elegant things you can do with programming. So look into that if you're interested. But this takes O of n time now. The other way to do this, and again, because I want to make sure we have plenty of time to go over the exam, I'm going to briefly go over this, is the way I showed the afternoon class how to do this, which is that I'm going to use something called memoization, which is my preferred method, which is a bit more intuitive to us, for me to understand at least, which is the idea here is that what I do is that to calculate my Fibonacci number, what I do is that the problem with these recursive call was that I was redoing all the work, right? So let's stop redoing the work. So as we calculate the nth Fibonacci number, let's store the Fibonacci numbers that we calculate. So here I store the Fibonacci numbers in an array. If I'm calculating the nth Fibonacci number, what I do is that I calculate I have a variable for the n minus 1 Fibonacci number and the nth minus 2 Fibonacci number. First off, of course, if I hit my base case, I just return 1, right? But if I'm not in my base case, if I'm something like the 3rd or 5th or the 100th Fibonacci number, what I do is I create a variable for the nth minus 1 and the nth minus 2 Fibonacci numbers, and I ask, okay, does my array have that number in it? Oh, it does? I'll store it. Otherwise, I'll calculate it and, sorry, I won't store it here. I'll retrieve it if I already have it. Otherwise, what I'll do is I'll calculate it, and then I'm going to store the result in my array so that I can use it later, right? So, and so I do that for the nth minus 2 as well. And then I just return n minus 1 plus n minus 2 over here. So notice that the recursive calls are still there. They're just if I haven't already calculated it. So now if I run this, the fib of using memoization, boom, no problem calculating the 50th Fibonacci number. No problem calculating the 100th Fibonacci number. No problem whatsoever, right? And the reason is because here I'm doing what's a very common trade-off to do, which is I'm trading trading space for time. Essentially, I'm using a little extra space for time as well. And the tail recursion does that a bit as well, with basically because it's storing extra stuff in the parameters, but it's not too much, right? Here we're creating an array, and we're not creating multiple arrays, right? It's the same array because we're just with arrays when you copy it, right? When you pass it into a method, you don't actually copy the array. You copy the reference to that array, right? In C, this would be passing the pointer along, right? And the nice feature about Java is that if it's an object, well, those objects can be monstrous, so we don't want to actually accidentally copy those over. We're going to copy the references for those monstrous objects over. So this is a technique called memoization. You'll learn more about it in 3223 if you want. But just know that basically if your problem is you're redoing work, stop redoing the work, right? It's a pretty easy solution. So let's actually look at some at the next topic, which is recursive array search. Well, that's what it says. It's binary search. That's what it's called. Binary search is basically the best way to do searching. It's basically the gold standard for searching. And today we're also going to learn something else. We're going to learn what logarithms actually mean. Just like we didn't learn the formal definition, for the formal mathematical definition for what big O meant, but we got a feeling for what it meant, right? We're actually going to get I understand intuitively now what log of n means, right? Rather than saying, I have to calculate like the exponents and figure out what power raised to the... No, none of that. Logarithms are way easier than that, and I don't know why they're not taught like this. So maybe because my method is a lie, but it works, so I mean... It does not matter if the cat is white or black. All that matters is that if it catches mice, it is a good cat. I heard that on the radio. So let's see. So here we go. So searching an array can be accomplished using recursion. Easiest way to do linear search, we're not even going to bother dealing with that. Linear search basically says how do you search for an item? Well, I'm going to look at the item I'm currently at. Right? If this isn't the item I'm looking for, I'm going to search the rest of the list, right? Starting at the first item of the rest of the list, right? Or as we know how to do it, to search for an item, we'll just iterate through the list and check every item, right? We'll just simply check every item in the list. How long does this take? It takes O of n time, right? That means that basically if there's n items, worst case scenario, I check all the items in the list, find it at the last position, or I don't find it at all, right? Worst case scenario, I have to check n items. Average case scenario, it's somewhere in the list randomly, sometimes in the beginning, sometimes in the end, sometimes in the middle, but on average, somewhere in the middle, because if you run this a bunch of times with a bunch of random numbers, it's going to end up somewhere in the middle. So I have to search half the list, which is another linear relationship, right? The other way, so the best case scenario is I find it immediately, but that's never going to happen, so we kind of ignore it, right? Now, granted, this is what you have to do sometimes, because when you have an unsorted, a bunch of unsorted data, this is what you have to do. It's the best way to do it if you have a bunch of unsorted data. However, if your data is sorted, so first off, your data has to be able to be sorted, right? It has to be able to be put in order. And if it's sorted, well, we can do something a bit more clever, right? Binary search algorithm. It goes into all this detailed stuff. Honestly, it's easier to understand by playing a game. So let's play a game. We already know how to play it, believe it or not. So the game is as follows. You pick a number between 1 and 100. Okay, I've got it stuck in my mind. I'm not going to switch it. So I'll even write it behind here just to make, if you want to double check, right? So that you guys, just to show that I won't be teaching, cheating. So I'm thinking of a number between 1 and 100. Guess the number, and I'll tell you if my number is lower or higher than yours, or if you got it right. Okay? So between 100, let's go. Sorry? 51. Okay, my number is bigger than 51. 75. It's bigger than 75.
97.
It's lower than 97. 80. It's lower than 80.
78.
Lower than 78.
77.
It is 77. All right. So there were some good calls and some not so good calls there. Okay. So let's go ahead and start. You started, though, with 51. 50 or 51 is the correct choice to start with. Why? It's in the middle of 1 to 100, right? Between middle. So what's the consequence of you choosing 51 as your first guess? What does that tell you when I say that my number is higher than 51? Sorry to put you on the spot like this. Okay. Anyone? What? Yes.
You only have to search through half.
Right. I only have to search through half this remaining stuff now. By choosing 51, all the stuff less than 51, I can automatically rule out. I can by guessing 51 and me telling you that it's higher than 51, I have ruled out in one check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Skip a few to 51. Okay. So and I've ruled out. So I've ruled out 1 through 50, the numbers beforehand, and 51 itself, leaving 52 through 100 left. Somebody else guessed 75, which is not a bad guess, right? Because that's in the middle. That's roughly between 50 and 100. So 75 is a good area for there. And maybe if you don't want to do the math to figure out why you're exactly in the middle, 75 is not bad. So why 75 again? Because again, it's in the middle. And by me saying that it's larger than 75, we know it's no longer between 52 and 75, right? Now the range is now a quarter of our original search space, right? It is 76 through 100, right? So let's think about that for a second. I could have used a linear searching algorithm to do this, by the way. I could have asked 1 higher, 2 higher, 3 higher, 4 higher, 5 higher. That would have worked, right? That is a algorithm. It would have solved the problem. People would have looked at you like an idiot, but it would have solved the problem. And at the end of the day, that matters a lot of the time. But it would not done so in the most optimal manner possible, right? So, on the other hand, the idea here is that we were able to split up our search space in half each time. And this is what we call a log base 2 or a log of n algorithm. When we talk about logs in computer science, right, we're going to be talking about base 2. And by the way, just go ahead and pull it up. He told you 77. I'm a man of my word, except when I'm not. Okay, so log base 2. So when we're dealing with in computer science, log means base 2. Always assume I'm talking about base 2. And even if you're not sure, a lot of times in computer science we have a special symbol, just like ln for natural log, right? The log base e. A lot of times we'll just abbreviate it to LG. Apparently, I don't know. This is what I've heard from the internet. And as Abraham Lincoln has said, you can trust anything you want on the internet. So log of n, log base 2. I'll use that if I really need specific. But right now we're going to deal with log base 2. Okay, log of n. So big O of log of n means that it grows logarithmically. But what does that mean? Well, this search algorithm we created was log base n. And what was special about it? We weren't searching through it sequentially. What we were doing, we were asking a question, right? And we were cutting the search space in half each time, right? So what we were doing was that basically we asked this, and we were able to say, we rule out this entire search space, right? And then we asked the second question, and we ruled out another quarter of the search space, right? We ruled out half of the search space, then we ruled out a quarter. Or another way to think of it is that we were looking at half the search space, and then we had the whole search space, then we had half, then we had a quarter. Each time we make a step, each time we ask a question, we eliminate half the spaces we want to look at, right? That's kind of the strategy we're looking for here, right? So the next question would have been to say, okay, what's between 76 and 100? How many numbers are there between there? 76 and 100. So there's 4 to bring you to 80, and then 20 more, right? Sometimes it's easier to add up to figure that out. So 76. So that's 24. So in the middle, let's say 12 over. So 76 plus 12 would have brought me to 88. So 88 would have been the next good guess, and I would have told you lower, which would have ruled out this 1/8 of it. Okay. So each time we make a guess, we are cutting it in half. So that's what a log n algorithm amounts to. Every time we make every step of the algorithm, we cut our search space in half, right? In a linear algorithm, every time we advance, we cut our, if we're searching for something, in a linear search, we cut our search space by 1 every step, for every 1 step we take, right? So that brings us into a good way of thinking of algorithms, right? A good way to think about algorithms, right, is to think, well, at least for log base 2, is to think of the amount of times I can divide a pile in half and then divide those piles in half until I get to 1, right? For example, what is, I told you I would not do exponents, but as I said, I'm only a man of word, except when I'm not. So to the 4th is what? 16, right? And we know from math that log base 2 of 16, right, is equal to log base 2 of 2 to the 4th, which means it's 4, right? But how can we do that without like doing that calculation, right? The question, well, let's split it and see how many times we can split it in half, okay? Now, mind you, it gets a bit ickier when we're dealing with non-integer numbers, right? And something we can't divide in half, but for figuring out what we need, it's a good idea. So 16 can be split into half, right? Into 2 8s, right? And what about those 8s? Well, we can split the 8s into half to form 4. I'll just go ahead and split one of them, right? Because it will just copy itself on the other side, right? And can we split that 4 into half? Yes, we can. 2 and 2. And what about those 2s? We can split those into half evenly, right? So we could split 16 into half once, twice, 3 times, 4 times. So a log at base 2 basically asks the question, how many times can I evenly split this number into half, right? Let's go ahead and look at, if you look, and if you just ask that question to like some number like 256, which is 2 to the 8th power, right? You'll see that I can split into 128s, then to 64s, then to 32s, then to 16s, right? Right? It works. It's a really interesting way that it works. Okay, so it's easy to, so in that case, what would log base 3 be asking? Let's just extrapolate here. If log base 2 is splitting stuff, is asking how many times I can split something evenly into halves, what is log base 3 asking? And how many times I can do it into thirds? Let's try it with tenths, because that's a bit easier, with log base 10, because that's a bit easier, right? How many times can I split this into tenths, into piles of even piles of 10, right? So I can split 1,000 into hundreds, into 10 piles of 100 each, right? And I can split those hundreds into 10 piles of tens, right? And I can split those tens into 10 piles of ones. So at that point, I'm done, right? So I could do 1 split, 2 split, 3 split. And right, if you remember, 10 to the 3rd is 1,000. So that's a pretty intuitive way to think of logarithms without having to get our hands too dirty, right? So, and we see that a lot when we deal with anything that has a log n or n log n, that we're splitting stuff in half. Okay? Does that make sense? Okay. So awesome. I was able to teach a bit of math, and who knows, it may universe if that was the case. So let's see. Am I recording through my microphone on this? I think I am. Let's turn this off. Oh, here it picked up again. So there we go. So hopefully this has good reception on it. If not, don't worry. I've already done this lecture once. That's why I like this class. I get to do 2 recordings. And remember, I've split, I don't know if I told you guys, but I've split the playlists now. So it's divided into the evening class playlist and the morning afternoon class playlist. So that's better organized, and you don't have to go searching for your lectures anymore. It's also for my sanity. So I'm not doing it for you. It's for my sanity. All right, so binary search works like this. So we need a base case, right? We need
or base cases in this case, because in this case we have two base cases. I gotta say case a lot. So the base cases are, the first case is that basically the array or the subarray that I'm searching is empty, right? If the array or the subarray I'm searching for the item for is empty, then that's easy. I just simply say it doesn't exist. The other base case is that the item I'm looking at, that's the item I want, right? I found the item. Like when somebody guessed 77, that was the base case, right? That was the item. The item I was thinking of was the item that you guessed. Okay? So the idea behind binary search is that rather than doing all this madness of looking for the first element and then the next element and the next element and the next element, we're going to look at the middle, and then we're going to decide to look either to the side that's less than or the side that's greater than. And so a good example of this, another example of this is that basically we're looking for Dustin, right? This is a bunch of sorted names. Caveat, remember, I said this works, it has to be sorted, right? So Dustin comes before Elliot. So if Dustin is in this list, it needs to be in the first three elements, right? So then we look at Karen, Debbie, and Dustin. We compare Dustin to the middle element of this. Well, Dustin would come after Debbie if it's in the list. So we search to the right, which has only one space left. So we check them all. So we check Dustin to Debbie, and we see that basically we were able to find it in 3 steps. Mind you, we would have found it in 3 steps anyway, right? It's hard to show this that this works on with small examples because you can normally find your small examples pretty quick. But the algorithm is as follows: if the array is empty, we return -1 because that's the way of saying the array that the index that you're looking for doesn't exist. We're returning the index of the item we're finding. If the middle element is the target we're looking for, then that's the other base case. So we return that index. Otherwise, if the item we're looking for is less than the middle element, recursively search all the items to the left. Otherwise, recursively search all the items to the right. So we'll figure out how to do left and right in a bit. But this is really efficient. When we get with 32,000 elements, that's going to take only 16 probes. It's got 1 because we've got to do these calls in there. But let's go ahead and do one more example on the board. Okay? We're going to do one example on the board here. Okay? And I'm going to, because I'm lazy, I'm going to skip a few numbers. So let's say I want to look for the number 13. So 0, 1, 2, 5. Now the numbers don't have, right? They don't have to be the case of they all have to be in sequence, right? They just have to be in order, right? So I'm allowed to skip 3, 4, and 4 here. All this works on anything that is sorted, right? So 1, 2, 3, 12, 13. So that's index 0, 1, 2, 3, 4, 5. So I'm going to go ahead and do 15, 20, 6, 7, and I'm going to go ahead and just simply skip a few, all the way up to maybe 100 over here at index 16. So don't worry if you can't see that there's nothing over there, except I'm saying that basically this is index 15, that we've got 16 items in here, right? Does that make sense? We've got 16 items in here. So we've got 16 items in here. Let's go ahead and do this algorithm. So we want to search for the number 13. Okay? So we say that this is the start of the area we're searching. And what we do is we define the end of the area we're searching. Okay? Start and end. So my start is, the starting index of this array that I'm searching is index 0. The end is 15. And what I need to do is I got to calculate the middle. What is the middle index? Because you can just because we're human, we can kind of just look and say, yeah, about there's the middle, right? Computer doesn't get to do that. They actually have to we have to give them numbers. So, so we got to come up with a number, and that's basically that it should be the start plus the end divided by 2. So in that case, it's 0 plus 15 divided by 2. That gives us 7.5. So we got to come up with a rule. Do we want to round up or do we want to round down? we're just going to round down because we're lazy, right? And Java can just simply do that with division, right? When we're dividing integers, Java automatically rounds down. So we'll say the middle index is 7, which is why I stopped at 7. So now we ask, okay, the number we're looking for, 13, is that less than, greater than, or equal to 20? It's less than 20. So we can ignore now everything above 7, index 7. So we're about to, so now our range is that of items we're gonna recurse over the range 0 through 7. Not actually 0 through 7, right? Because we just checked 7, right? We don't care about 7 anymore. Since 13 is less than the index 7, we don't have to, we know it's not equal, so we can ignore it. So now we can just search the range 0 through 6. That makes sense to everybody? So 0 through 6, what's the middle of that? Well, that's pretty easy to figure out. There's 3 here and 3 here, so the middle should be 3. 0 plus 6 is 0 plus 6 divided by 2, that's 3. Okay? Is the item at index 3, which is 5, is that smaller or bigger? It's smaller than 13. So 13 needs to be is it going to be in indices 4, 5, and 6, or 6, right? So now my range is going to be from 4 to 6. What's the middle of that? 4 plus 6 divided by 2 is 5. So we check index 5. That's got my 13 in it. And I return 13. This makes sense to everybody? So let's go ahead and code this up. So we're going to do our base cases first, and then we do our recursive cases. It's always easy to do that. Okay, so recursion, evening, there we go. So let's do recursion examples in the evening. Okay, public, static, void, int, search. So we're going to search, well, I want to search some list of numbers, right? But it's got to be sorted. If some list of, well, it actually doesn't have to be numbers. It could be strings or anything, which means that I have to use, does anybody remember? The comparable interface. The comparable interface. Remember how I mentioned it a while back with the comparable interface? So this is where I actually have to use it. So I want to search. So what I do over here is, since this is going to be dealing with generics, I want this to work on anything that can be sorted or anything that can be put in an order. We use a special interface in Java for that. E extends comparable E. So what this does is that this ensures that this method can only be called on things that are sortable, that can be sorted, like integers or strings or doubles, but maybe not on something else that can't be sorted. Like, I don't know if scanner can be sorted or anything like that. So, but that seems like a good thing, in the type of thing that can't be sorted. Or generic objects, those things can't be sorted, right? So E extends comparable. So we take, so that all that does, so we only have to put the extends comparable here. And what that does is that basically says that any E that you see in this method, it's going to be comparable. So here's my list of E's, which we know is comparable. I'm going to look for a target, and then I need to provide 2 parameters, the start and the end, right? The start index and the end index, okay? So the first thing we need to know is whether or not the section of the array we're searching for is out of bounds or not, okay? And we can do that by checking start and end. If start and end, right, starts over here and ends over here, normally, right, the start is to the left and end is to the right, right? But eventually the range shrinks like this, and if they ever cross, that means that basically that the area I'm searching between them doesn't exist anymore. So if start is greater than end, that indicates that we cross the stream somewhere, that they're no longer a valid area to look for. So we'll say return 1. Let's return -1 to say that it's an invalid index. Okay. Now the other thing we have to do is now, check the middle. Well, first we have to figure out what the middle is, right? So let's figure out int middle is equal to, as we put, it's start plus end divided by 2. That's the index, right? Now this is actually a common mistake that I see a lot of the time. I've made it a number of times myself. Start plus end divided by 2. Can anybody tell me what my problem is here? What did I do? Yep, PEMDAS is my problem. My algorithm, my what's going on in my head is correct, but what's going on over here, what I wrote, is not correct, right? PEMDAS is the problem because we divided by 2 and then we added. So start plus n divide by 2. Always be careful when you're doing division, right? I mean, and multiplication, but this happens way more often with division because with multiplication you can move stuff around a bit easier. So that's the middle index, start plus n divided by 2, okay? And E item is list.get the item at the middle. Okay, so I'm just going to grab that so I don't have to keep calling it. All right, so now what am I going to do? Okay, well, now I'm going to use the compare to method, right? And the compare to, remember, will return a number. So I'll say int comparison is equal to target.compare to item. So it's going to return, so this will return 0 if the target and the item are equal to each other, okay? It will return a negative number if target is less than the item, and it will return a positive number if target is greater than the item. And always be sure that you've got them in the right order, right? Because, you know, if this returns negative for target.compare to item, it'll return a positive for item.compare to target. So always be sure that you put it in the order you intended to put it in, right? I've done that before. It's annoying. Okay, so if comparison is equal to 0, that's our other base case, right? And this is a bit weird because our base cases are kind of separated here, right? So if comparison is equal to 0, return middle, right? Because we found it. We found our item. That's a very easy distinction to make, right? This was all very easy stuff. Check the middle item. If it's equal to, return it. That's base case, right? No, it didn't. There was no like questions that really particularly tough questions we had to ask. Else, if the comparison is less than 0, right? If we got a negative number back from our comparison, well, then that means we have to search the left half of the array. So we have to search, and we got to figure out, we got to return the result of searching this list. And remember, it's got to take 4 arguments here. So I'm going to still be searching the same list, right? I'm going to still be searching it for the same target. So that was easy. So now I have to figure out just where I'm going to start. Well, if I'm going to the left, right? If I'm searching the left half of the array, my start hasn't really changed, right? When I had this example up here, when I looked at 7 and said, or index 7, and I said 13 is less than 20, so we got to search to the left, right? My start remained at 0, right? So the start doesn't change when you go to the left, right? Or it doesn't change when you go to the left. Yes. So the start is still the same. So what changes is the end. And rather than searching through the end, we search up to in the middle -1 because we can exclude the middle now, right? That makes sense to everybody? So, right, when we were looking through indices 0 through 15, what we ended up doing once we made our decision to cut out all the items to the right, we said let's look through 0 through 6, right? So the middle, which was 7, -1, which was 6. Okay, and now we'll just put an else here because if it's not equal to and it's not greater than, sorry, not less than, then comparison has to be greater than, which means we have to search to the right. So we can do some copy pasting here. Return search the list for the target, and I'm going to search up to the end because in this case when I'm searching to the right, the end doesn't change. My starting point now changes. And I'm going to start looking at the middle, but I've already looked at the middle, so I can look 1 item to the right, so I can add 1 to that. So I'm going to go ahead and, let's see. Oh, yep. So I'm going to go ahead and copy my test over from yesterday's class because why bother, rewriting the bit of code that basically just adds a bunch of stuff to my list. So, okay, so what we're going to do over here is copy this in. So what are we dealing with? We are dealing with an so what we're dealing with is that we're going to create, let's go ahead and create an array list of just to hold items, and I'm going to create a random number generator, and this time I'm providing it with what's called a seed, and that just simply means that basically that I wanted to generate randomly distributed numbers, but for the purposes of reproducibility, I want to produce the same numbers each time. What is that sequence of numbers? It's determined by the seed, which is normally randomly generated by like using some weird data like the last the nanoseconds digits of your system's time clock and stuff like that. Maybe like where your cursor is or some other random data. Okay, so probably not where your cursor is because a lot of times it's going to be over here, but a lot of other stuff that can be anything that can be randomly generated. Okay, so then what I do is I go ahead and I add a million random numbers to this. I generate a million random numbers, and if I generate a number that's less than 0, I multiply it by. If I generate a negative random number, I multiply that negative random number by -1 to turn it positive, right? So this just simply turns it positive, and I add it. And then I'm going to add the number 13 to this, and then I'm going to sort it because otherwise it's going to be this test would be worthless because binary search, remember, only works on sorted on things that are sorted. Okay. Now then I have to provide it with I want to start at index 0, and then I want to go up to index. How big is this? It's 1,000,000. So I want to do what? I want to do list L.length or L.size -1. And honestly, that's not the greatest idea to let the user make the user provide all this data right over here to search for it. It should be search, not binary search over here. Right here, because the user could mess up and they could put in the wrong range or something. So instead what we do to basically hide the fact that we need these parameters is we'll do what's called a wrapper method. So all we do is that we turn this private. Instead, what we do is that we create public static, and static e extends comparable e. Oh, one too many there. Okay, int search, and all it does is that it takes in the list. It only takes in 2 parameters now: the list and the target. And what it does is that it goes ahead and calls and returns our recursive method and sets it up with all the correct parameters. So e search for list target starting at index 0 and list.size -1. Okay. So now let's go ahead, and this actually takes a long time to generate only because I'm generating a bunch of random numbers and sorting them. But then it's able to find it very quickly. Oh, I was searching for the number 10,000. So let's go ahead and reduce the size of this. So 10,000 numbers. Boom, it finds it really quickly. Finds it at index 0 really quickly. So this works very, very quickly with finding it. Yes.
What is the efficiency of the collection of sort?
So this is a n log n sorting algorithm. I think it's Tim sort. It's either quicksort or Tim sort. Those are the 2 sorts that are typically used. So this binary search will find stuff really quickly. The time that it took was actually generating, adding a bunch of items and generating that space. Okay. With that, let's go ahead and work And by the way, there's a binary search. So binary search is the best way to search stuff if it's sorted. Now, mind you, if you can't sort your data or the data you're getting is unsorted, then tough luck, right? You got to use a linear search instead. But it's available in the arrays class with the arrays.binary search function. So you can just search anything that way. So now let's talk about recursive data structures. So we were talking about recursive algorithms. Let's talk about recursive data structures. And the way this is going to work is that we're going to review linked lists. Okay? So a recursive data structure is like kind of that Russian nesting doll thing. Inside of each Russian nesting doll is a tinier Russian nesting doll, right? So, and it's going to look very different, but the algorithms are going to look a lot more elegant for what we're doing. So linked lists and trees are actually, they can be defined. They don't have to be, but they can be defined as recursive data structures. Now we're going to learn about trees as a recursive data structure. Okay? And these recursive methods will provide a very natural mechanism for processing these things. So honestly, a linked list, it's easy to see when you draw it that it's actually recursive. Okay? So a linked list is a recursive data structure because what it is that inside every linked list is smaller and smaller linked lists. That's a recursive definition right there, right? Each linked list can be defined as follows. Right, here's a linked list of 4 items. I like using 4 because that's generally the right amount of data there, right? And we can define this linked list as this is the head of the linked list. And what it points to is a node that is the head of its own linked list. Does that make sense to everybody? This linked list is the head of a linked list, and it points to another node which is the head of its own linked list, right? And this is so this one in the box, that's a linked list of size 3, right? Does that make sense? And this guy, he points to a linked list, the head of another linked list, and he's a linked list of size 2. This guy's a linked list of size 1, and he points to an empty linked list, right? He points to the last guy on the item, he points to a linked list of null. Yes?
Is it a linked list of linked lists, or is it just a linked list of heads pointing?
It's a linked list of heads, right? So these are each individually nodes, right? But each node is the head of its own linked list. You know, have you heard of the expression? Basically, every captain is the king of his own ship, right? So, it doesn't matter. If you're the captain, you outrank everybody. It doesn't matter if you get into light bulb and you're of low rank. You're now the captain, right? Because it's your lifeboat. This is kind of what's going on here, right? We've got a big data structure, and he's pointing to a slightly smaller version of this data structure, which is pointing to a slightly smaller version, right? Or the head of the slightly smaller version, right? So we don't actually code this in where basically with the recursion. We just simply say that we just simply think this way, and then when we do add and remove, we're going to use this thinking. Okay, does that make sense? We're going to use this thinking because the code isn't going to look actually any too different. I've already loaded the code up, and I don't really see the need to copy it over. So here's a recursive linked list that's provided by the author of the textbook. Okay, so as far as we're concerned, it really doesn't change what we were looking at. The main points of it haven't really changed. A linked list, recursive, it is a linked list of stuff. It has a node head, and it has the same node class. Private eData with a node, and it's pointing to the next node. That really should have that in there. Okay. And it has a constructor where it takes in a data item, and then they like to put in a second constructor where basically you can initialize the next node in there. I prefer to do code my list without this statement because it makes you have to manipulate the next pointers directly, right? So that basically when we deal with statements where we have to do .next, it makes more sense because we've been using .next the entire time. All right, so let's look at basically how this recursive thinking that each node is the head of a linked list to our advantage. We're going to look at a really easy method first, which is we're going to, just like we did a very bad size of a length of a string algorithm, we're going to do a not constant time size algorithm, but we're going to do a linear time size algorithm. So this is the wrapper method for this. To calculate the size of the list of the linked list, we ask what is the size of the linked list starting at head. Okay? So, and notice over here that we have head as a local variable here, right? Because we are finding the size of a list. The head of the current list is the parameter. Notice how this is the local variable head and not the instance variable head. Okay? So first, if the head of, so let's just look at this. For recursive cases, we need a recursive case and a base case. The base case here is that if the linked list is empty because we don't have a head, well, then the linked list size is 0, right? So we return 0. Otherwise, we do it with the whole lazy recursion matter that we've been talking about. Well, I know how big I am. I'm 1. I don't know how big the linked list after me is, though, right? So I'm going to ask the head of the linked list after me, head.next, to calculate his size. Does that make sense? So what's going to happen over here is that this head, he's going to say, well, my size is 1 plus the size of the linked list after me. So we're going to call head.next, size of head.next. And this head is going to go, oh, well, I'm size 1 plus whatever the size of the linked list is after me. So I'll return 1 plus whatever that is. He's going to go, well, I'm size 1 plus whatever the size of the linked list after me is. He's going to go, well, I'm size 1 plus whatever the size of head.next is. Head.next is null, so that returns 0. He goes, oh, so I guess my linked list size is 1. So he returns 1 to him, who goes, so that's 1 plus 1, which is 2. And he gets 2 back, so he returns 3. And head goes, and the original head goes, aha! So the linked list after me, that was size 3. So I return myself plus the size of the linked list after me, which is 4. Right? That makes sense? Yes.
And there's no like size method.
We didn't keep a track of a size variable, right? Okay, we didn't have a size variable here. So this was a bad way to calculate size because we have to count. It takes O of n time, right? We have to do all the passes there. Yes.
So if you had a double linked list, could you use binary search? Because you have.
It's kind of tricky to do that because I mean you have to iterate to the middle, right? You have to find the middle, right? So it gets a bit trickier with doing binary search on a linked list. There's some weird things that make binary search harder, but as you may have discovered on the practice exam, although I think I gave the incorrect instructions on there, doing a merge, like doing merge sort is extremely easy with linked lists because that's kind of efficient. But anyway, so let's look at the toString method. Public string toString. So if we want to turn this linked list into a string, we turn the head of the link. We call toString on head, which says, given the head of the linked list, we'll return a string that represents this linked list. So if the head is null, right, if there isn't a linked list there, it's an empty linked list, we're going to return the empty string because there's nothing in it. Otherwise, what I'm going to return is the head.data plus an arrow just to indicate the link, right? And then I'm going to attach that to whatever the string representation of the linked list after me is, right? Yes.
And that's just for like the linked list that's next to it, not
right.
all of them.
Well, it's going to be all of them, right? Because that's the way recursion. Basically, from my perspective, so if I'm the head, right? So if this is A, B, C, D in here, right? From his perspective, his work is I calculate A, right? Because that's easy. And I don't know what's behind me. I don't know what's in the linked list after me because I don't want to know. It's their business, right? So he says, he just simply passes the command to this guy and says, give me the toString of your linked list, okay? And what he's going to do is that he's going to pass that to C, who's going to pass it to D. D will return D to C, which will return CD, which will turn BCD, right? So he's asking the next guy to do the same thing, right? He's giving the same command. The only difference is that he's one less. All right. So let's look at how add is done in a linked list manner. Okay. So wrapper method. So here we start with, we want to add data. Add this data to a linked list. And notice that this is an add method. It doesn't care what the index is here. Okay. It's just simply add it to the end of the linked list. That's all this add method is. Okay. We're not going to deal with like adding to a certain index. You can imagine though that would just involve using a parameter as a counter. Okay. But here we don't need any like current. We don't need a current.next or anything. It actually ends up being really elegant, which says, okay, so let's look at our over here. So if head is equal to null, right? If I'm trying to add this item to the linked list, to the linked list. If the linked list is empty, well, that new item is now, it gets a node and is now the head of the linked list, right? That's pretty simple. Otherwise, I'm going to add this data to the end of the linked list starting at head. This is what it says. So I'm going to add, so this private method, so this passes that over here. We say, I want to add this data to the end of the linked list starting at head. Okay? And we just use the same, and so now we ask every node that exists. So sorry, every head of a linked list. We ask the head of this linked list. Okay, do I have space after me? If I have space after me, well, then I'm at the end of the link. I've got no linked list after me, so I'll make this guy my next node, right? Right. If my head.next is if the head of this linked list doesn't have anything after him, I'm going to go ahead and add it to the after me, which means I'm adding it to the end of the linked list. Otherwise, I do have something after me. So what do? I call, well, I don't have an empty space, so I tell the linked list after me, hey, I hope you have extra space because I want you to add this data to the end of the linked list. Right, so over here, if we were trying to add E, we'd try adding E here, and you'd go, nope, I can't, I don't have space. So add E to B. And B's like, nope, I don't have any space, so I'm going to add E to the linked list starting at C. And C's like, nope, I'm add it to the linked list starting at D. And D's like, nope, wait, what? I have space? Oh, I guess okay. So then he adds it to the end there, and that's done. Make sense? Yes.
Is that on the linked list of the heads or?
There's only nodes, and every node, right, is the head of its own linked list starting from its position, right? Right. Every node. So he's the head of a linked list of size 4. He's the head of a linked list size 3, 2, and 1. That makes sense?
And that one is added into that one,
right?
And that's it.
Right. It's all one list, right? But each node. But when we look at each node, we think of each node as the head of its own linked list. That's the idea. It's all one linked list. But we think for the purposes of the algorithm of writing the algorithms, we just treat every node as the head of its own linked list, right? Just as we're doing binary search, we're not actually searching a new array, a new smaller array. We're just searching a subsection of the array. We're treating each array, we're treating it like it's an array of half the size, even though we didn't actually cut it up and cut that array up. All right, so now going on to remove the method, to the remove method. So now we want to remove some data from our linked list, okay? So we don't want to remove that at some index. We're just given an item. I want you to remove this item from the linked list, okay? The first occurrence of it. Okay, so let's look at our wrapper method. Obviously, if the head is null, the linked list is completely empty. We can't remove anything from it, so return false. Otherwise, if the first item in the linked list, the head of the whole linked list has that item, well, we just remove it by going head is equal to head.next, right? Otherwise, the way we need to do this is that we remove out data, and we ask, hey, linked list after me. You need to, or linked list after me, you need to remove this, right? And remember, because we need to keep track of the node after us when or remember how when we remove an item at index I, we want to get the node at I minus 1, right? in order to make sure we can do this successfully, what we'll do is that we will pass in the previous node. So here, to remove, what we're going to do is that we are going to remove the first occurrence of out data from the list. The parameters are the head of the current linked list that we're looking at, right? Every node thinks it's the head of its own linked list. The predecessor of that list, so in other words, the guy in front of me. So, and then the data itself. So if the node I'm looking at, so if head is equal to null, that's the base case. We got all the way to the end. It's not there. The other base case is that the head we're looking at, the head of the linked list, has the data we want to remove. So what we do is that we say the predecessor, right, the guy before me, he points to the guy after me. So he skips over me now, right? Pred.next is equal to head.next. So that removes the head of this linked list and replaces it with head.next. Otherwise, if I'm not empty and I don't have it, I tell the linked list after me, you got to remove this guy from you, and I'm going to pass myself along for the ride, just so you have a reference to me in case you need to remove yourself. So this is a completely different way to think of linked lists, but it's amazingly elegant, right? Amazingly short. But at the same time, it's recursion and it's 630, so it's not necessarily the easiest way to learn the linked list for the first time. But looking at it the second time, this is a very interesting way and a completely valid way to write a linked list. So I see that basically this is getting technical and very boring. So now let's get to the point where we get to say, okay, what's the point? Where's the fun stuff? Well, congratulations, we reached the fun stuff, which is puzzles. So let's look at the very classic puzzle called the Towers of Hanoi. Okay, how many of you have seen these? These are also called the Towers of Brahma. But it's a puzzle. So the idea is that we want to take these 3 pegs. So we have 3 pegs and a bunch of disks. In this case, we have 3. And we want to move these 3 pegs from the leftmost peg to the rightmost peg. And you're like, okay, that's really easy. I'm just going to pick those up and just put them down on the right peg. Problem done. Easy puzzle. Well, wait, I tell you, there are rules. Okay? You can only move one peg at a time. One disk at a time. And you're like, okay, so we can just treat these pegs as stacks. So I pop the top of L and put it on M, right? So I pop everything from L and push it onto M. So basically, I flip it over onto M, right? And then I flip it over onto R, right? I flip it over onto the middle, and then you go, okay, that's really a boring puzzle. And I go, wait, there's still one more rule, okay? And the rule is that you can't put a bigger disk on a smaller disk. You can only move one at a time, and you can't put a bigger disk on a smaller disk. And at this point, you go, oh, okay, wait, no, it's hard. It's not trivial anymore, right? So how do we take all the disks over here and move them over to here? Now, when I do this on paper or over here, I typically do this using numbers. And you may be wondering, okay, where the heck is recursion for this, right? We'll get there. But when I do I'll use numbers for disks instead. So 1, 2, 3, here's my middle, and here's my right. So I want to move everything over here, right? The idea here is I got to move all these guys over. And if you puzzle it out, you're like, okay, there's 3 disks. We can obviously just experiment here and like maybe try to move stuff over to here. So maybe if I move 1 here, and then 2 here, and then 1 here, and then, oh, I want to move 3 over there. So let's start over. Instead of moving 1 to the middle, I'll move 1 over here, right? Then put 2 here, and then 1 over here. And now that's out of the way, right? Okay. And then I'm going to put, I guess I don't want to put 1 there because I need to put 2 there. So I'm going to move 1 over here, right? Makes sense? Everybody following me so far? 2. So it's got all the characteristics of a good puzzle. A very small number of simple rules. Now this is only 3 disks, but Towers of Hanoi can be played with any number of disks, which is fantastic. So and it's a very well-known problem. So let's go ahead and turn off automatic scene switcher for a second, so that we can stop it. And now I'll do just the screen. So we can open up Firefox so that we can look at Towers of Hanoi, which for a page with puzzles, for puzzles, it's actually quite extensive on the math here, right? It's talking about algorithms, and then it's got H's and stuff, and then recursive implementation and code. This is going from a puzzle to something crazy. But here's a Towers of Hanoi with 8 disks, right? That seems a bit more intimidating. And it's and here's one at a museum in Mexico City, which I like this one. Look how big that one is. It gets even more intimidating when you zoom in, right? And here's people playing with and here's, it's just a very nice interactive panel. It's a very good puzzle because it teaches you about recursion, believe it or not. But in order to see the recursion, we have to go deeper, so to speak. We have to go up to we have to go to a different, level of recursion. So we have to start going to more disks. Okay? So let's go from 1 to 3 to 4 disks, right? Over here. Okay, and now it's a bit hard to experiment, but let's just think about this from the strategy to what we learned last time, okay? What I learned is that basically when I was doing 3, right, on my first try, I moved 1 over to here, right, and then 2 over to here, and then I moved 1 back over here, and I realized I was stuck, right, because I wanted to move 3 over to here, right? What I really needed, and what I needed to do was move 1 and 2 over to here, right? In other words, I needed to take the top disks off and move them over here out of the way so I could move the bottom disk over, right? And then I could move the top disks over to here, right? So now and the same theory applies to when I'm doing 4 disks, right? Which is that I need to, what I need to do to get halfway through the puzzle, right? I got to take these top 3 disks and move them over to here, and then I can move this 4th disk, this bottommost disk, over here. So that gets me to another question, right? So how do I move these 3 disks over here, right? We started at asking, how do I move these 4 disks over to here? And we just changed that to, how do I move these 3 disks over to here? Well, in order to do that, I need to move these top 2 disks out of the way over here so that the bottom disk can go over here so I can move these top 2 over to here, right? I have to take 1 and 2, move them over here so I can put 3 over here, and then I can put 1 and 2 on top. Got to figure out the moves to do that, right? Hold on a second. I'm in the middle of class. Is everything okay? Okay, bye. Sorry. I'm a family member, so just you never know what happens. So okay, sorry about that. So we were looking at 1, 2, 3. So we were saying to move what we had to do to get this over is that we had to take this disk and move it over to here. But in order to do that, we have to move these 3 out of the way, right, to here. And to move these 3 disks out of the way, I had to move these 2 over here, right? So it's becoming recursive, right? I mean, you can see if I were to move this up to 5 disks, right? The goal is then I have to move 1, 2, 3, 4 over to here so I can move 5 over to here, and then I have to move 1, 2, 3, 4 on top there. Well, how do I get 1, 2, 3, 4 over here? Well, to get 1, 2, 3, 4 over here, I have to move 1, 2, 3 over to here so I can move 4 over to here, right? And then I take those and move those back on top. Everybody see that? And in order to move 1, 2, 3, well, how do I do that? I have to put 2 over here so I can get the 3 over here so I can put the 2 over. So let's go back to our 4 disk. So what I have to do is that I have to get the 4 over to here. To do that, I have to get the 3 over here. To do that, I have to get the 2 over to here, which means I got to go 1 over here, so 2 over here, then put the 1 on top. Then I put the 3 over here, which means I put the 1 over here to get that out of the way so I can put the 2 here, so I can put the 1 here, so I can put the 4 here. Right, so now I have to move 1, 2, 3 over to here, which means I have to take this guy, so 3 has to go here, right? So I have to take 1 and 2, move this over here, which means 1 goes over here, 2 goes over here, 1 goes over here, right? Which means I go 3 over here, 1, 2, right? The recursive algorithm. Despite the speed of which I'm speaking, you know, and the only reason I can do that fast is because I've done it like a million times in class, because I really enjoyed this problem. So let's look at the algorithm for this. Okay, let's go ahead and look at the algorithm for this on the board. The algorithm to move, I want to move n disks, right, from the start to the end, right? I want to move one n disks from the start to the end, and then I've got this third disk over here, which I'll call aux or auxiliary, right? Extra space, right? So, so in order to do that, well, let's see. We got to. If this is recursion, I've got to come up with a base case. If n equals 0. Okay, I'm done, right? If there's no disks, then stop doing stuff, right? Okay, else, okay, what's my plan? My plan was I needed to move, if I'm moving n disks from the start to the end, the first thing I have to do is I have to move the top n minus 1 disks out of the way, right? I have to move the top n minus 1 disk out of the way, and I got to move them from start, and I move them out of the way onto the auxiliary space, right? And then I'm going to use that end, that destination as kind of the storage area to do all my extra work on, right? Okay, so now I've moved all those n disks out of the way. So now, end dot push, and I believe I'll call it append here. Right, we're gonna add to the end start dot pop, right? Make sense? Start dot pop. So we're gonna pop off on the start and add it to the end of n, right? On top of n. Okay, and then so now that we moved the n minus 1 disk over, we put 1 disk on top of n. Now we need to move n minus 1 disks from, we move them to auxiliary, right? We want to move them from auxiliary to the end, and then I guess start goes here. Okay? And then, okay, so there's my pseudocode, right, for this problem. So all that's left is for me to translate this this pseudocode into a working program. All right, it's a Python program now. I kid you not, that is a working Python program. And honestly, it's not really that hard to do that in Java either. It's actually a ridiculously simple algorithm. It looks ridiculously simple. Mine is a bit more, slightly more verbose than the one they have over here. But def move n disks from source to target. If there's disks to move n minus 1 of them from the source to auxiliary to the target. Target.append source.pop. Print out a progress to show how that line by line move, and then remove the remaining ones, and then we start the call. There's also a non-recursive solution, but it's not nearly as fun as this, which is that basically, how does it work? Well, you make the legal move you take the top disk from A to B. Sorry, make the legal move from pegs A and B. So if you can move a disk from A to B, you make that. If you can make it from B to A, though, you make that instead, right? Only one of those moves is going to be legal. Then you make you make a legal move from A to C. So you make so from start and the middle, from middle and the end, from the start and the end, and the middle from the end. And then you just completely repeat this process, right? So you just completely repeat it, and it will actually solve it for any even number of disks. This takes, so how many moves does Towers normally take? It takes 2 to the n minus 1 moves, if you, at least. That assumes you do it perfectly. Doesn't matter what solution you need. Now, for those of you having trouble following, though, why I like this puzzle and why I love the Wikipedia page, why I like this Wikipedia page over here, is this over here, where we're going to see the recursive solution, which is actually not an image. It's more than just an image. It's like it breaks it up into the recursion. So how do I move 4 disks from here to here? Well, the first thing I have to do is move the top 3 disks. Then I move the bottom disk over, and then I move the top 3 disks on top. Okay, so how do I move those top 3 disks over? Well, you move the top 2 disks out of the way. Then you move that 3rd disk into the middle, and then you move the 2 disks on top. And then you can break that up into those individual moves, right? So it's each of these, as you can see, each problem reduces to a smaller problem, right? The problem of moving 4 disks is how do I move 3 disks out of the way, move the bottommost disk, and move the 3 disks that I moved out of the way back on top, right? Moving 5 disks is solving 4 disks. Moving 6 disks, I have to solve 5, right? And you can see basically, and it takes 2 to the nth power because remember, we're doing, just like the Fibonacci problem when we originally showed you, we're making 2 recursive calls, right? I have a move n-1 and a move n-1 over there. Now, I typically give this as a homework problem, and it honestly isn't too bad because most students, they just translate the pseudocode. It isn't too bad, but recursion is this really nifty, powerful tool. You know, this will look like a really intimidating puzzle. I mean, let's see. So actually, we've got some really cool code here that we can show you. That the professors who wrote this book, and the professors who wrote the book are former Temple professors. They had this really cool program that I'll just pull up for you, where they actually, you know, made a nice graphical show of it. And you can download this from like the course website, or sorry, from the book's resources if you look it up. But here, recursion.towers annoy, extended James phrase, and we're just going to run it. Boom. And here's a size 20 towers of annoy, and if I just play it, it solves the problem. I mean, it goes way too fast for us, so let's go ahead and, let's go ahead and set the number of rings maybe to 5 rings, okay? Oh, it's nice and resized, and let's go ahead and see the singles, right? The first move we need to do is we need to take, the problem is that we want to take these 4 disks over and move them over here so that disk 5 can go over, which means these 3 disks have to go over here, which means these 2 disks have to go over here, which means 1 should go and start at C. So, right? That means we can move 2 over to here. Single step. There we go. Which means 1 has to go over here, so we can move it out of the way for 3. Which means that we need to go and take, so now we need to make sure we can move 4 over to here. So that means moving 1 over there, or sorry, 1 over here, 2 over here, so we can put 1 on top over there, so we can move 4 over there. So now we got to move 1, 2, 3 over to here, which means we got to move 1 and 2 out of the way over here. So 1 has to go over to here, so 2 can go over here, so 1 can go over here, so 3 can go over there. Now 1's got to go out of the way so we can get 2 on top. Right? So let's go ahead and play slowly. So this is again a recursive. The problem is just being solved by recursion, and the code doesn't look like the code should work, right? It looks way too simple for such a complicated problem. But I keep telling you, a lot of problems in computer science are a lot harder than they look, especially if you use recursion when you can just break it down into much simpler problems. Okay. So what other problems are we going to tackle of our course here? Well, one thing we're going to do you're going to do later as a homework, because I always give this as a homework, is the 8 queens problem. Thought I put down 8 queens puzzle. So it has its own Wikipedia page. It is a chess puzzle. So and how many of you have not played chess before? Okay, don't worry, not a requirement. So all that you have to understand is how queens work, which is that basically a queen is a piece that can capture anything in the same row, the same column, and the same diagonal as it. The 8 queens puzzle asks us, let me go ahead and zoom in here. The 8 queens puzzle asks us, let's place 8 queens on the chessboard, which is an 8 by 8 grid. So so you can represent that by 8 by 8 array. So place 8 queens on a chessboard such that no queen can capture one another. So if we can see, so by seeing this, we see that no queen is on the same diagonal, the same row, or the same column as each other. How do you solve this? We use something called recursive backtracking, which is the technique we use to solve a puzzle. Only we use the stack there. We're going to actually directly use recursion to solve this puzzle. It's actually such a powerful technique that you can use it on other puzzles like Sudoku. But I'll get into that when we get back next week. For right now, I'm sure you're all feeling crazy anxious about the test, so I'm going to go and work on the problems with you guys, and hopefully I can solve them. What we're going to do is that we're going to take a break, but there's a quiz on Recursion that should be posted online. The password is 12345. So I think I've used that before, but if I haven't, then I've used it somewhere before. But the password is 12345. So take it. We'll be resuming at 7 o'clock, and I'll get myself ready to work on these problems. If I don't have the time to do them, I'll try my best to get to solve the problems so that they get up online for you.